Like I said in the previous video, we found lots of derivatives using the chain rule. This video, we're going to start looking at quick applications. Now, when our inside function was inside of a power rule, what happened? Well, when we did examples like this h of x and this m of x, when we had a power rule being our outside function, we applied the rule to find derivatives of the power rule. So we took 7, multiplied it out front times the 10. This stayed the same, raised to a 6th power, and then we multiplied times the derivative of the inside function. And while I was doing that, I wrote 10 times u to the 7th. So I had this, y equals 10 times something to the 7th power. And essentially what we did is we took y prime equals 70 u to the 6th power and then multiplied that times the derivative of the inside function. If I wanted to symbolize that with a u, I could just take that as u prime. So you can see kind of what's going on if I'm willing to utilize the letter u as a variable for my inside function. I take the power rule just like I normally would, and then I multiply that result by u prime. Similarly, with y equals natural log of u, the derivative was 1 over u multiplied times the derivative of the inside function. And I said if you wanted to rewrite that, which we always ended up rewriting, you could write that as u prime over u. So you can see that if we're willing to use u as our inside function, we can think about the chain rule in some quicker formats. And that leads us to looking at some quick applications of the chain rule. Here, we're taking derivatives of common chain rule environments. So the derivative of u to a power is going to be that power comes out front, u to the power minus 1, multiplied times u prime. Derivative of e to a power, well, derivative of e to a power is just e to that power, and then we multiply that times derivative of the inside function. So derivative of e to a power is derivative of the power times e to that power. Derivative of natural log of an inside function is derivative of u divided by u. We've seen derivatives of sine and cosine and tangent before. So if we take the derivative of sine, you get cosine. So if we take the derivative of sine of a function, we get cosine of that function multiplied times the derivative of the inside function. Derivative of cosine is negative sine. So derivative of cosine of a function is negative sine of that function times the derivative of the inside function. We know that derivative of tangent is secant squared. So derivative of tangent of a function is secant squared of the function times derivative of the inside function. These quick applications of the chain rule can help us out a lot. Let's use those quick applications to determine how to quickly find derivatives of these exponential functions. In this third function, the variable a represents any real number. F of x equals e to the 7x. The derivative of that, think y equals e to the power u. That means y prime is equal to u prime times e to the power u, which means my f of x has derivative of f prime of x equals derivative of the inside function is 7 e to the 7x. So derivative of f is 7 e to the 7x. In a similar way, if I think of this as 5 times e to the u, derivative of the inside piece is just 10. So derivative of g of x is going to be take 10 times 5, that's 50. Let me write that down in 2 steps. So I'm going to take the 10, that's derivative of the inside function. I'm going to multiply it out front times e to that same function. So we get 50 e to the 10x as the derivative of g of x. Notice that each time we have a coefficient in front of x, what's really happening is we're just multiplying the front by that variable a. So h of x equals e to the ax has derivative, which is equal to a times e to the ax. That's all due to the shortcut rules there, or the quick rules. By the way, that works for any linear function. So as long as you have e to a power, which is a linear function, the derivative of that is the slope of the linear function multiplied times e to that linear function. Usually you see this rule as e to the ax has derivative a times e to the ax. That's going to be an important one moving forward because we're going to see a lot of those examples later on in the material. I want you to try to find the general rule of taking sine of ax and do that by first taking the derivative of sine of 8x, then taking 2 sine of 9x, and then figure out what would happen if you took the derivative of sine of ax.